So if you just watched the last video, or if you've been reading this chapter, you'll remember that the problem we have here is that when we're trying to explain and predict who will and won't purchase one of our bikes, there are many different independent variables that could predict this, and they all have some type of crossover or interlap between them, as well as with the Y variable, a purchased bike. What we want to know is exactly how much does each one, or do each one of these independent variables overlap or predict purchased bike with after partialing out or controlling for the effects of the other independent variables. Then we're going to actually use those weights that we come up with, these correlation coefficients, I'm going to start calling them weights, to help us predict new data and predict who it will and won't purchase a bike. So follow along with me. If you don't have it open, go ahead and download and open the Bike Buyers data set. Remember, you can find it up here at the top of the chapter, towards the top right there. And you should have, if you haven't already, created a numeric version of this data where we have marital status, gender, income, all these things, everything except for occupation and region converted to numeric data. So we're not going to be able to use these two in our what we call multivariate regression model. Now, you actually can include this type of data in regression models, and it's not that hard. But to keep things simple for this class, I'm simply going to leave those ones out. So to help make this simpler, I'm going to cut and insert these cells over here. I want all of my dependent variables to be contiguous here in the spreadsheet. Actually, it doesn't really matter if our dependent variable is next to it or not, but whatever. What I'm going to do next, click on Data. Oh, and it looks like I need to add in my solver and data analysis tool pack again. If you lost yours, if you've closed Excel and for some reason it's not on there again, just follow along with me. Go to File, Options, Add-ins. Wait, there we go. Excel add-ins go. Check Data Analysis Tool Pack. OK. And they should pop up right here in just a second. OK, here it is, Data Analysis. So let's open this. We're going to go to Regression. OK. Now, as with an ANOVA, we have an output or a Y variable, and then we have, instead of like the ANOVA where there's only one X variable, we have a range of X variables. So for the Y variable, go ahead and select this purchase bike column. So I selected the label and I hit Control-Shift down, check labels so it knows the first row is a label. Click here on the input X range. Go up to the top, include the labels here, and go all the way over from marital status to commute distance. So these are 1, 2, 3, 4, 5, 6, 7, 8 independent variables. Did I count that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry. Anyway, so I've got K1 to K1001, B1 to J1001. Okay. Output range. Make sure you click here in this text box. Otherwise, if you click on the sheet, it's going to overwrite your Y input range. And just come over here to something like O2 and click that cell to output to and hit OK. So the analysis itself is pretty quick. It doesn't take long for this to come up. Let me explain what you're seeing here, and then we'll teach you how to make a prediction calculator out of this. So first thing, you should recognize this. R square is our coefficient of determination. Now, R square is going to range from 0 to 1, and we'll interpret it as a percent. So in this case, the R squared is 9.26%. And you may think, well, that's not very high. However, remember, if I'm simply going to guess what people's purchase bike Y value will be, I have two options, either yes or no. So you might think I've got a 50-50 chance of predicting whether or not they'll purchase a bike. Think of this 9% as 9% better than a 50-50 chance of purchasing a bike. Now that is not a perfectly accurate, true to form definition of R squared. The statistics purists would throw up at hearing that definition, but for all intents and purposes, that's exactly what it is. We're able to explain about 9% of the variance in purchased bike better than if we were to simply randomly guess. So that's actually worth quite a bit of money. To put it in perspective, Netflix, and I've told some of my students this story, but Netflix recently paid millions of dollars to anyone who could improve the R squared value of their ability to predict what movie or TV show you want to watch next. If they could improve that R squared value by 2%, Netflix paid millions and opened up this as kind of like a competition to anyone who could do it. So 9% is worth a lot of money. Anyway, so I'm going to bold that as something you're going to want to remember. Down here you'll see an ANOVA. Now we've done ANOVA, and for some weird reason, I don't know why they did this, but this value here they call significance F, it means p-value. And this is, what do you call it, scientific notation. The negative 17 means it's like 0.000, count 17 zeros. It's very significant. In other words, this is far less than 0.05. But to interpret this properly, all this means is that the combination of these independent variables together does have some significant effect on the independent variable called purchase bike. So next, I want you to take a look at two things on this table. This is what we're going to care about for this class. The coefficients and the p-values. Let's convert all of these numbers quickly into something with just a couple decimal places, make it a bit easier to read. Okay, that'll do. Actually, I'll give it one more. So, intercept. We're going to come back to that in just a moment. Ignore that for now. Intercept is not a variable. So if you get a test question that says which variables are significant, and one of your options includes intercept, you know it's a trick question. Intercept is not a variable. Rather, if you go back to our the reading, and particularly the part where it talks about slope. Look at these lines. This is a negative correlation here between some x variable and some y variable. The intercept is where the line of best fit crosses the y-axis, meaning if I'm going to predict what someone's y value is based on the x value, I have to start by adding whatever the distance or the difference between where that line of best fit crosses the y-axis with 0. So that's part of my y equals mx plus b formula. I've got to add in that intercept to my prediction in order to get an accurate prediction for y. So back here, this intercept is simply telling you that based on this combination of variables, if I were to plot a 1, 2, 3, 4, 5, 6, 7, 9, 10-dimensional graph and draw a line of best fit through that 10-dimensional graph, because each one of these is its own dimension, that line would cross at 0.642 on the y-axis. Okay, so we'll come back to that. Here's our variables. These coefficients, think of a definition for coefficient as the correlation between marital status and the y variable, which is purchase bike, the correlation between those two after accounting for the correlations of all other variables. So you probably still have your correlation table up. I'm going to throw mine, add one on here real quick, because I want you to see the difference now between correlation and coefficient. So I'm going to, well, I guess I didn't need to do that. Let me hit data, data analysis, correlation, okay. Let's go ahead and select all these. Yep, labels in first row. Let's output this. Oh, there we go. Let's output this somewhere over here. I'll put it right down below. Uh-oh, did I include something with non-numeric data? Labels in first row. What did I include on accident? Oh, whoops, it went all the way over to L. Sorry. Okay, there we go. Okay, let's scroll down. Here it printed out our correlation table. I'm going to change these decimals, make this a bit smaller. Okay, so the correlation between marital status and purchase bike, which is right here, is negative 0.0109. The coefficient is bigger, it's 0.13. And that's okay. The reason why that can be bigger is imagine, oops, let me go back here to this diagram. Imagine if commute distance is taking out or explaining this portion of purchase bike, then the correlation left on education, although it's not going to include this part right here, there's a smaller remaining percent of purchase bike left over to explain. So the part that is crossing over with purchase bike is now a bigger percentage of the remaining whole, that after removing or accounting for this portion that's explained by other variables. So, in other words, this regression weight can increase from the original correlation table as well as decrease. So, marital status, the negative 0.13, how do I interpret that? What that means is, as purchase bike shifts from 0 to 1, meaning they actually purchase a bike, negative means marital status goes from 1 to 0. So marital status has two values, 1 and 0. Well, in this case, 1 is married, single is not married. So what that means then, by a negative sign, is that as people become married, they are less likely to purchase a bike. Or people that don't purchase a bike are more likely to be single. There's an inverse relationship between those numbers. Gender. Do we care about gender? No, because look at the p-value. That's well above 0.05. So in other words, whether they're male or female has no effect on whether or not they purchase a bike. Awesome. We're going to ignore gender from now on then. Income. Income has such a huge effect, but look, the coefficient itself is super small. Well, let's just give ourselves some more decimal places because the actual number itself is there. It's not 0. It's a very small weight. The reason why that weight is so small is because the data we get is so large. So the weight needs to be very, very small to compensate for how huge this income data is compared to all the other numbers. These are all zeros, ones, fours. At most we get a 73, but then income's in the thousands. So imagine we basically divided by 1,000 on this weight to make it to make it accurate compared to all the other types of data. But p-value says income, yes, has a huge effect on whether or not they purchase a bike. Cars, the weight's very small. Children, weight is small, but it's below 0.05, so children matters. The more children people have, since this coefficient is negative, the more children they have, the fewer bikes they purchase. Cars, same thing. And that makes sense. As people have more kids, they probably have less money. Cars, as they own more cars, they purchase fewer bikes. And that p-value is significant. Also makes sense. If people are purchasing bikes to commute to work, then as they have cars, they're less likely to need a bike. Age doesn't matter. Education, surprisingly, doesn't matter. Well, look down here at the correlation. Education on purchased bike is 0.14. That's a decent-sized correlation. Compare that to something like, let's see here. What else is a 0.14? Commute distance is a negative 0.14. Identical correlation strengths between education and purchase bike and commute distance and purchase bike. However, look, commute distance is significant and education is not. That's because commute distance, after accounting for education, commute distance still explained a large chunk. The remaining overlap here was still quite large, and my guess is there are other variables that overlap with purchase bike that also overlap with education, like income, which may not overlap with commute distance. So in the end, the true effect of education is actually much smaller than this once we add in all the other variables. So the remaining part that was just due to education was too small to be significant. Okay, homeowner, not significant. We're not going to worry about it. Commute distance, like we just talked about, is. So now we know which variables matter when determining who purchases a bike. So what I might do is use this information, one, to help me make some decisions about who I should target, what types of bikes I should sell. If people are buying fewer bikes when they have further to commute, so let's see, the larger my commute distance is, the less likely I buy a bike. Then maybe it's because the types of bikes I'm selling are primarily used by commuters. Maybe what that tells me then is I should start offering different lines of bikes to people who want them for purposes other than commuting. Maybe it's time to open up a line of mountain bikes that people can use that are clearly recreational, or something like that. So this gives you great information to predict and understand who it is that wants to buy your bikes, but we can make this even more useful. So let's say, for example, that I have this data and I don't know whether or not they purchased a bike. I'm going to hide these. Hide. Rather, This is information about customers that I bought from a consulting firm. That's very common. There are companies out there that simply aggregate consumer data. You know, those companies that put like a free car or a free four-wheeler or something like that in the mall, and they want you to fill out your information to enter yourself in a drawing to get it. What they're doing is they give out a car which maybe costs $20,000, and the information that you give them is worth about 50 grand for them to sell to other companies to use. So it's just easy money for them. So we've gone to one of those companies and we've bought all of your data, which is very easy to do. And you've never come into our store before, and we're trying to decide if we should market to you or not. If we should try to send you a mailer or somehow market to you to buy a bike. So what I want to do is, based on these regression weights or coefficients, I want to look at your actual data and predict whether or not you're going to purchase a bike from me. So I actually want to insert a column real fast. Let me unhide those. Let's insert a column right here. We're going to call it prediction. And then I'll go back and hide these ones once again. Hide. Okay. So here's how it works. Think back to our slope formula here on MyEducator. So remember, the formula for slope is y equals mx plus b, where m, this one right here, is the slope of the line. X is the x value, or in our case, the actual value of a variable. And then plus b, that's our intercept, where it crosses the y-axis. So we're going to use that formula, but instead of y equals mx plus b, let me give you an example here. Y equals mx plus b, where m is going to be the slope or the regression weight of a variable, and x is someone's actual value for marital status. So let's say we want to predict this first person right here. I'm going to freeze that pane. View, freeze, top row. Okay, so someone's actual marital status is 1. If they're married, I'm going to plug that 1 in for x, and m is going to be negative 0.03. So if I was just going to predict someone's, whether or not they purchase a bike based on their marital status, I'd say y, their prediction, is going to equal that regression weight right here, negative 0.13, times whether or not they're married. So if they're married, that's a 1, plus b is my intercept right here, 0.64, that's close enough. So that's my formula to predict whether or not they'll purchase a bike. In this case, that's going to equal, I'll put it over here, y equals, right align that guy. I'm going to say negative, this one's going to be equals negative 0.13 times 1 plus 0.64. Whoops, what did I do there? Plus, let me take that off. Accept that correction, yes, there we go. So let me go back over here and show you my formula once again. Okay. Y equals, and it's the regression weight, negative 0.13, times the actual value for someone. This is, and 1 means yes, they are married. I'm going to try and predict for person 11,000 here. So I'm going to call this ID 11,000. Or sorry, yeah, there we go. So for that person, I'm going to predict their purchase bike status, or Y, is a 6.51. Now purchase bike is it's either a 0 or a 1. So if it's closer to 0, then I'm going to say no, they won't purchase a bike. If it's closer to 1, yes, they will purchase a bike. In this case, it's way over 1. It's 6.15. So I'm going to say yes, based on their marital status, this person is absolutely going to purchase a bike from me. However, I've got data on everything else too. So let me pick a person here who's not married. Let's do person 11090. So for ID 11090, Y equals, let's right align that. Their formula is going to equal negative 0.13 times 0 plus 0.64. Okay, in this case, 0.64 is also closer to 1 than it is to 0. So no matter what, whether they're a 0 or a 1, it's always going to predict that everyone's going to purchase a bike. That's because this weight is based on including all these other variables in the formula. So here's what we have to do. Instead of using y equals mx plus b, I'm going to move these up here. We're going to use y equals m x plus mx plus mx. That's 3 plus mx plus mx. Alright, time to do some copying and pasting to make this go a little faster. That's 5, there we go, plus b. This is our formula because we can't include just one of these variables, like marital status. We've got to include the slope and the actual value for every one of these variables. So each of the m's are going to refer to each of these regression weights, each of these coefficients right here. And each of the x's refer to the actual values in one of these rows that we want to predict for. So let's do this for person 11,000 and then 11,090. So what this is going to mean is that we're going to redo this formula as y equals, now the first m we have right, it is negative 0.13 times 1, but now we got to add that 2, and I'm going to start just doing things in parentheses like this to make life a bit easier. So gender we said is not significant, but I'm just going to go ahead and include all of them anyway because the weights, these coefficients were built on including everything in the model. So let's go ahead and include it. Negative 0.012 times, is this person is a 0, so I'm going to put 0. I think in ours, I think 0 is male, plus I'm going to put in a bunch of these. This is going to be for income plus children plus cars age, there we go, plus cars, age, education, homeowner, commute distance. So I've got to plug in the weight times the actual value for each one of these things. So a quick way to do that that's not going to take forever is I'm going to instead delete that, and right here my prediction is going to equal each of these weights. I'm going to copy this, and then right here I'm going to paste and transpose this little icon right here. So it's going to paste those weights across this. Let's reduce the number of decimal places so it's easy to interpret. Alright, and actually I'm going to move this right up here to this cell. Okay, now I'm going to plug in the actual values for, oops, let me go back over here one. There we go. No borders. I'm going to plug in the actual values for these two people. So here's person 11,000. Copy. Let's paste just the values. Oh, I see why I left a space. Sorry. No, I do want these over here on that one. And then let's do the same thing for person 11,090. Paste. Okay. Oops. Let me grab that one more time. Paste values. Okay, so I'm going to multiply each of the actual values. So these values right here are the x values listed here in this formula, whereas these regression coefficients are the slopes or the weights for each of these variables after controlling for all other variables. So what I want here is the actual predicted value by multiplying 1 times this, 0 times this, 90,000 times this, and then don't forget we've got to add back in the intercept, which we find right here, and come up with our actual prediction. So I'm going to use the sum product function because it's a nice little shortcut to do this exact thing. I simply grab one array, comma, the other array. And then I need to make sure that I add back in this plus b right here. That's my intercept right there. And I'm going to F4 that so that it always stays on that cell. Also, I want to F4 my weights so that when I copy this down, it stays on that spot. So copy this down. There. These predictions both 0.71. The way I interpret that is that since 0.71 is closer to 1, which indicates purchase bike, than it is to 0, which indicates doesn't purchase bike, then I'm going to predict that these two people will purchase a bike. So I can now predict if I get anyone who matches these data points for their various demographics, then I'm going to predict yes, they will purchase a bike, and I'm going to target those people in future advertisements. Now let's take this a step further. What I want to do is copy this function right over here into this prediction column. Let me expand out this cell a bit. And I'm going to adjust my formula so that my actual x values are these right here in that cell, and then it's still going to multiply them by these weights, and it's still going to add in this intercept right here. Enter. So now I have the predicted value for every person. So if you're still asking yourself, why did we do all this in the first place? What is this good for? Let's say now that you as a store owner have a special deal or sale that you think is going to bring in some new customers. And let's say that these are your potential new customers here, people who've never come into your store before but live in your area or something like that. You bought this data from a consulting firm. Now that you've predicted the likelihood that each of them will purchase a bike, let's sort it largest to smallest. And let's say I want to start experimenting by going door to door or something like that, hiring someone to go door to door to offer a special sale to 10 people on my list. Well, we may as well try this with the 10 most likely people to purchase a bike, which are these right here.